Hi guys, so today we're going to be talking about word problems which follow exponential models. You've probably heard of some examples in class. The most common examples that they do are half-life, doubling time, like the amount of time it takes for a population to double, or compounding money, like if you're getting compound interest on money. So some of the common equations they give out for these first three, half-life we have written here. This equation is written in books a lot. Doubling time looks like that, kind of the same thing as half-life, but they put a 2 in the parentheses instead of a 1/2. And then continuous compounding of money. You've probably heard to that referred to as PERT, P-E to the R-T. All three of those equations can actually be lumped into a more generic equation, which is this right here. So for any word problem that's half-life, doubling time, continuous compounding, we could just use this more generic equation over here, which is A of t, and let's label what each thing is. A of t is always the future amount of whatever it is that you're talking about. So A of t is future amount. A0 is always the initial amount. The k is sometimes given to you. Like if they say what percent it's growing at, that's going to be the k. But a lot of times they don't tell you that. So let's just call k our constant. And then the t is time. And the k, if the problem is exponential growth, the k will come out positive. But if it's exponential decay, where something is decreasing, then the k will come out negative. And you don't really even have to worry about that because that will just happen when you solve it in your problem. And then these other two things I wrote down here, they usually teach you first. These two equations are just for like basic annual growth and annual decay. Like if they say a population is growing at 3% per year, then you would use the basic growth. Or like if they said a car that you purchased is going to lose its value at 4% per year, you would do the second equation for the decay. So let's flip to our next page here and try an actual problem. So this one is a problem about a medicine entering the bloodstream. It gradually dilutes, decreasing exponentially with a half-life of 3 days. Now, it's a half-life problem, so I'm going to use that more generic formula just to show you how it works. A of t equals A0 e to the kt. Now, if you read through the whole problem, they didn't tell you at what percent it's decreasing, so we do not know the k ahead of time. And they also did not tell you an initial amount of medicine that's in the bloodstream, and there's very few numbers that they did give you. So what I like to do for these problems is for the initial amount, we'll just pretend that it was 100. So pretend that it was 100 units, like 100 grams, 100 milligrams, whatever, that part doesn't matter. And that will help us going forward. So if they're saying that the half-life is 3 days, that would mean that when time is 3 days, the future amount would be 50, because we're pretending that the initial amount is 100. So we can plug those numbers in. 50 would go here, equals 100 goes here, e, we don't know k, but in this scenario that we're currently doing, the time is 3 days. So now we can just solve this for k, and this will be the k that we use to answer the next part of the question. So 1/2 equals e to the 3k. Then I need to use a logarithm. I'm going to do the ln of 1/2 equals 3k. So that part is just changing the exponential into logarithmic form. And then if I divide both sides by 3, This is going to give me k. So doing that in the calculator, I get negative 0.231 equals k. So this is the k for the entire problem now. So now to go back and answer their original question, it said how many days does it take for 90% of the original amount to dilute? Well, if our original amount is 100, let's just jot that here, our original amount we're saying was 100. If 90% of that has diluted, then the future amount would only be 10, because starting with 100 and 90% of it going away would leave you with 10. So this is 90% has diluted. So this gives us our numbers to plug in to solve for time. So we're going to say 10 equals 100, e to the k, which we now know is negative 0.231, times t. So we're solving for t. So divide both sides by 100. This gives us 0.1 equals e to the negative 0.231t. And again, we have to do a logarithm to solve for the t that's in the exponent. So that's the ln of 0.1 equals negative 0.231t. So that is, again, taking exponential form and changing it into logarithmic form. And then just divide both sides by negative 0.231. So we'll do that on a calculator. And we get 9.968 equals t. Right there. So our final answer would be 9.968 days, because that's what time was measured in for this problem, equals t. So it takes that many days for 90% of the medicine to dilute in the bloodstream. Okay, now moving on to our last problem here. I decided to give an annual growth problem so that we could use the basic growth model that I wrote on the first page of notes. So the population of a certain city is growing at 3% per year, so that tells us that the R is 0.03. The beginning population was 12,500, they said, so A0 is 12,500. And then it says in how many years would it reach 33,000? So the future amount is going to be 33,000. And in how many years? That's the time, so that's what we're solving for. So now we can just plug in every number that we have. So this would be 33,000 for the future amount. A0 was 12,500. 1 plus r, so that's going to be 1 plus 0.03 to the t we don't know. So now we're solving for t. So divide both sides by 12,500. And you can do that in a calculator. So that is 2.64. That cancels. And then over here we could add, that's 1.03 altogether to the t. And then again, we need to change this to logarithm form. So it's log 1.03 of 2.64 equals t. Just remember, we're doing this a lot. We're changing exponential form into logarithm form. Just remember, the base 1.03 is the base of the logarithm. And then the number on the other side of the equals, the 2.64, that is the argument of the logarithm. And finally, the exponent, so this t right here, is always what gets isolated. It's always alone. That's why using a logarithm is necessary and helpful, because it isolates the exponent and solves for it. So now I'll just do this logarithm in my calculator. and I get 32.84 equals t. And in this problem, time was years. So it's going to take 32.84 years before the population reaches a grand total of 33,000 people. And that is it. So I hope that helps.